เราจะพูดถึง particle physicist เนี่ยโอเคคือท่านคือดร. James Beacham มาจาก CERN European Organization for Nuclear Research เพราะฉะนั้นเขาจะมาพูดถึงวิทยาศาสตร์นะคะที่น่าสนใจว่าในโลกของเรามีอะไรบ้างนะคะ Our next speaker we will have Dr. James Beacham, the particle physicist from CERN, the European Organization for Nuclear Research. And I know it's a bit far-fetched, but we are talking about the future, so it's a very important question to ask ourselves, what's outside the universe? Let's listen to the answer.
What's outside of our universe? My friend Melody asked me this question when I was 8 years old. I usually had good answers for science questions. I was sort of a library guy. But this time, I had no idea what to say. The question was scary. I grew up in southern Utah, and this is in the western part of the United States. And this is the home of red rocks, hot, dry summer nights, and clear skies. And these are perfect conditions for stargazing. And as a kid, my friend Melody and I would bicycle out of town to get away from the lights of the city. And we would stare up at the sky, and we would ask each other questions about the universe. How big is the Earth? What is the sun made of? How far away is that galaxy there? Why can't I see a black hole? What's at the edge of the universe? When she asked me that one, I stopped and I thought about it, and I finally said, I don't know. And Melody said, my ancestors thought that the Earth was a big flat rock with a solid dome of sky above it, and the stars were painted on it. And we stared up at the dome of sky, and I said, well, I guess they didn't have telescopes back then, so I think that's a good first guess. But now that we know the universe is huge, I don't know what's at the edge of the universe. Melody was an indigenous Native American from a local tribe. I don't remember if she was Paiute or Navajo, and the other kids at school would sometimes make fun of Melody, calling her nasty names. She did not like tests, she did not like homework assignments, but she ran circles around the other kids in classroom discussions with the teacher. And there was a reason why she and I were friends, because Melody was never afraid to ask the big questions. And when she finally asked me, what's outside the universe? The question caught me off guard. Well, nothing. The universe is everything. And it doesn't make any sense to ask what's outside of everything. Everything is everything. Yeah, but if the universe has an edge, then there must be something beyond the edge, she reasoned. And we stared at the sky for a very long time, and finally I said, maybe there is no edge and no outside. And Melody said, yeah. Maybe the universe just goes on forever and ever, and that's everything there is. And after a long pause, I finally said, everything is terrifying. And as you can see, I was a very serious child, but maybe perhaps not completely serious, because for me, terrifying does not have to be a bad thing. But before we go too far, we have to answer one very important question. What is the universe? Picture the last time you were out in the wilderness and you looked up at the night sky. Thousands of pinpoints of light, photons, particles of light traveling from galaxies and stars thousands of light years away, a light year being the distance that light travels in 1 year, to finally reach Earth and smack into your eyeballs. When you look up in the night sky, you're looking backward in time. But look closer. In between those points of light, what do you see? It looks like empty black space, but it's not. Your eyes are pretty good photon detectors for one particular type of photon, but on cosmic scales, your eyes are terrible experimental apparatuses because they can only see a relatively narrow range of photon wavelengths, and there's so much more hitting our Earth than what you can see with your eyes. If you were to use humanity's best photon detectors, like satellite telescopes, you'd see hidden light, photons from stars and galaxies millions and billions of light years away, and eventually you would see something absolutely remarkable: the cosmic microwave background radiation, which is just a fancy word for light from when our universe was 100,000 years old. This is the closest thing we can get to a baby picture of our universe. But wait a minute, baby picture, a few 100,000 years old? That's a pretty old baby. Where's the light from before then? That light hasn't had time to reach us yet, and most of it never will. All of those galaxies we see in the sky, they're all moving away from each other in all directions. The universe is expanding. But you may have heard that phrase before, but what does it mean? The universe is expanding into what? Is our universe like a limp balloon put into a box, and then the balloon is blown up into the box? No. The universe is expanding into nothing. Space itself, the background metric spatial grid upon which everything rests, is being stretched. Two galaxies in our universe are like two pins stuck into a rubber sheet, which is being pulled from all directions. From the perspective of an ant on the sheet, nothing happened to make the pins move. Space itself, the sheet, is being stretched, and the distance between them is increasing. And, as you know, if everything is moving apart from each other right now, we can simply run the clock backwards, theoretically, and that means that at some point far, far back in time, 13.8 billion years ago, everything in the universe had to have been packed into a tiny, dense little point, which then started expanding. And this, as you know, is the Big Bang. But it's not just the fact that the universe has been expanding like that for 13.8 billion years. That's not the most important detail. There's so much that we can't explain if the universe has always expanded at a constant rate. For example, why does the stuff in that part of the sky look more or less like the stuff in that part of the sky? Why do we see big things in the universe at all, like galaxies or cosmic structures? They shouldn't even be there. Why does that cosmic microwave background radiation, the baby picture of the universe, why is it essentially uniform in temperature everywhere? Don't let the colors fool you. My astrophysics colleagues put those on there to show the small gradations, but it's essentially uniform in temperature. None of this makes any sense unless, right at the moment, of the universe's expansion, it did not just expand at a constant rate, but first insanely inflated before then tapering off to a much more gradual rate. And this insane inflation was not just some minor thing. Imagine if we took a horse and we magically inflated it to the size of the current observable universe in 10 to the minus 32 seconds. That's what inflation was like at the moment of the Big Bang. This inflation was much faster than the speed of light. And as you know, the only way we here on Earth can know that anything exists in the universe is if we receive a signal from it. Thus, at the moment of the Big Bang, when everything started inflating, most of the universe was completely separated from us forever and will never be able to contact it ever. This leaves us with a new concept of what the universe is, the concept of the observable universe, which is a tiny subset of volume defined by all of the stuff in the universe that could ever possibly send us a signal that we could receive, which must be a tiny subset of the entire universe, within which there must be a huge number of other observable universes for other observers, and we'll never be able to contact them or verify they exist ever. And it gets worse. If you look closely at the mathematics behind this idea, this absurd inflation of the fabric of space, it should go on forever. And that's weird because it leaves us with the conclusion that our universe, the thing that you live in, and the fabric of space itself, this sheet, can be thought of as two distinct things, because our universe stopped inflating and it tapered off to a much more gradual rate and has been going at a very gradual rate for billions of years. But the expansion of the fabric of space itself should go on infinitely forever. Our universe is almost like a little bubble that was popped into existence when the fabric of space started inflating and expanding. And if you look closely at that mathematics, and you should always look closely at mathematics, if you look closely, this inflation should go on infinitely forever. But in our universe, it didn't. This leaves us with the inescapable conclusion that if something happens once in infinity, it has to happen again and again and again. If our universe was popped into existence as a bubble, there must be an almost infinite number of other universes that were also popped into existence by this insane inflation of the fabric of space. In most of them, inflation probably never slowed down, and they're completely boring, empty voids, and you'd never want to hold a big digital conference there because no one would show up. But if our understanding of inflation is correct, there must be other universes like ours. In one of them, one of you wore different shoes here today. In another, coffee is pink. And in another, an Earth-like planet was obliterated by an asteroid just as protozoans started to evolve. If our understanding of the mathematics of what happened right at the Big Bang is correct, then this isn't just idle speculation, but is required by infinity. But I see the skeptical looks on your faces, and you're absolutely valid. These are valid response to what I'm saying, because I'm an experimentalist. You should be yelling at me right now. Come on, man, we need evidence, and you're right. This is just circumstantial at the moment. But it turns out it's not the only piece of circumstantial evidence that we have that makes us think that we might live in a multiverse. For example, our universe seems to be filled with magic numbers, these constants of nature that we but just measure, but we have no particular explanation for why their values are what they are, like the electron charge or the gravitational constant. They just seem to be put there for no reason at all. And one of them is very important to me and my colleagues. One of them is called the Higgs boson mass. And this was something that was discovered at the Large Hadron Collider by my colleagues and I back in 2012. And this Higgs boson particle, some of you may have heard of it described as the God particle. We don't use that phrase. The Higgs boson particle is a very important and very weird particle. A reminder, the Large Hadron Collider is a 27-kilometer circular tunnel on the border of France and Switzerland, 100 meters underground, and for comparison, this is what it would look like if it wrapped around Bangkok. It would be a very efficient subway system. It's a 27-kilometer circular tunnel on the border of France and Switzerland, 100 meters underground, and in this tunnel, we use superconducting magnets that are colder than outer space to accelerate protons. You're made of protons to almost the speed of light. And then we smash them into each other millions of times per second. And we collect a record of the debris of these collisions. And we sift through this data to look for evidence of new undiscovered particles that could help explain the biggest mysteries of nature. And when we finally turned this machine on and we took some data, we discovered a fantastic particle, and it was discovered by one of the experiments that I work on, which is called ATLAS, and it's 6 stories high, it's 46 meters long. It's really impressive to see, and in fact, I invite everyone in the audience to come to Switzerland. You get a chance to go downstairs and see it. This lucky guy got to stand there just as they were pulling in the rest of the stuff. You don't want to stand there when he's doing that. But so discovered at this Higgs boson particle in 2012, and it was an amazing discovery, and there was champagne and celebration and Nobel Prizes. It was a wonderful thing. But there was also a little bit of head scratching because, to be honest, we probably shouldn't have discovered this thing at all. There were a lot of things that we're still looking for at the Large Hadron Collider. It was not just this Higgs boson particle. There's so many open questions of nature, such as dark matter. Every single one of you right now, every second of every day, you have about 1 billion particles of dark matter flowing through your body, and you've never felt it. It's never affected you. It is not what gives you headaches or causes depression, I promise. But we know for a fact it has to exist because we see its effect on the cosmos in galaxies that are spinning much faster than they should. There's so many big open questions that we're trying to find the answers to with experiments like the Large Hadron Collider. And when we finally discovered this Higgs boson particle, again, it was a great celebration, but it also started to make us wonder, why did we find this particle at all? For the following reason. The largeness of experiments like the Large Hadron Collider, you might ask the question, why is it so large? It's large because the bigger the machine, the higher energy you can get to. Remember your high school physics, kinetic energy. If you take a particle and you make it go faster and faster and faster, it has more kinetic energy. And this is important because of Einstein's famous relation, E equals mc squared. E is the part we can control, but m is the part we don't control. M is a mass. It's a mass of a particle. And mass is not the same thing for particles that we use, and it's like, look at that massive building. Mass for a particle is just a property that's put there by nature, and we don't control it, we just measure it. And if nature has a particle with a mass m that's all the way up here, and we only build a collider that goes up to energy here, we'll never discover it and measure its properties. So that's why we need big machines. That's why the large part of the Large Hadron Collider comes in. But again, if you look closely at the mathematics, and you should always look closely at the mathematics, there's nothing to prevent the Higgs boson mass from being something gigantically huge, all the way over here, way outside of the range of the Large Hadron Collider. But we found the particle down here. We discovered its mass down at this end. That's really weird. What's holding the Higgs boson mass right here? It's almost as though there's some kind of quantum mechanical shelf that the Higgs boson is sitting on. And in a real sense, in a physical sense, this would correspond to a bunch of other particles that we would discover right around the same place as the Higgs boson. That would explain a lot. It would be great if we saw these particles. We do not see these particles at all at the Large Hadron Collider. This is a bizarre puzzle. What's holding the Higgs boson mass all the way over here? It's very, very good. And to be clear, it's very, very good that the Higgs boson, we found it where we did. Because if the Higgs boson had a completely different, or even a slightly different mass than what we measure, our universe would be a very, very different place. The Higgs boson particle is demonstration that something called the Higgs field exists. And the Higgs field is essentially an invisible jelly that permeates all of space all the time. You don't feel it, but your individual particles feel it. As they zip through the universe, a little bit of their energy is dragged by this jelly and stuck into a point, which we measure as mass. And that's good, because the electron, your body is swarming with electrons. If the electron did not feel the Higgs field, if there were no Higgs field, the electron would have a precisely zero mass, and that would be very bad. Because if the electron had a precisely zero mass, at the moment of the Big Bang, atoms would never have formed, and you and I would not be here to have this discussion. So it's good that the Higgs boson exists right where we found it. But what's holding the Higgs boson mass down there? I'm a physicist. I want an explanation for why. Maybe we just got lucky, but a very particular type of luck. Nature loves statistical distributions. I doubt you will hear a nerdier statement said all day today. Nature loves statistical distributions. The average heart rate of everyone in this room will be distributed as a Gaussian or normal distribution. If you stand on a street corner, and the rate with which cars will pass you will follow a Poisson distribution. In a sense, physics and math and statistics seem to transcend our universe. So what if our Higgs boson mass, this really, really fortunate, lucky thing, what if our mass is only one of an almost infinite number of possible values of this thing in a multiverse? In most of these other universes, the value of the Higgs boson mass was something totally different, and they're completely boring voids, and you'd never want to hold a digital conference there because no one would show up. But in ours, one of them had to be selected as the right one. Again, the lack of extra particles, extra discoveries at the Large Hadron Collider is not proof positive that we live in a multiverse, but it's another piece of circumstantial evidence that we should take this idea a little bit more seriously. But again, I see the skeptical looks on your faces, and you're absolutely justified. This is not proof. This is not evidence. How are you going to test this? I like the way you think, and in fact, we have a couple of ideas as to how to test this idea as to whether we live in a multiverse, but they are currently very difficult or technologically challenging to pull off. One way is that we can look for a bruise or bump on our universe. Remember those almost infinite number of other universes that popped into existence when the fabric of space inflated? What if two of them inflated right next to each other and bumped into each other? Could this be what this really dark blue spot is on the baby picture of the universe? When our universe started to expand, there was another one right next to it and they bumped into each other? The jury is still out as to whether this hypothesis fits the data better than some other one, but investigations are ongoing. Another way is to keep looking for those extra particles, aka my day job. So it turns out that it would be okay if we discovered these extra particles, this quantum mechanical shelf that the Higgs boson sits on. It's okay if we find them just outside of the range of the Large Hadron Collider. It would be a little bit weird, but at least we'd be very satisfied. We're like, oh, okay. We're pretty sure we don't live in a multiverse. We don't have to worry about that. Plans are underway right now for the next generation of particle physics collider, which will be 100 kilometers around, and I live kind of right in the top middle there, by the way. This would enable us to get to very high energies, and it would really help us understand a lot about the universe. But would that be enough? If we finally build this big thing, which is be in the next, say, 20, 30 years, would I finally be satisfied? Could I then come back to you and say, yes, we did not discover anything, therefore you live in a multiverse? No, that's not enough. We would have to go bigger. Why don't we instead build a particle collider that goes around the outer edge of the moon? This would enable us to get up to tens of thousands of times the energy. What if the particles are way up here and we need to build something gigantic to get up there? And you might think this sounds crazy, but think about it. There are lots of people that are interested in going back to the moon. Moon Express, the Google Lunar X Prize, these wealthy billionaires that want to go and start mining things on the moon. Why don't we do a science center instead? So I know what I want with this particle collider on the moon, but I can't do it by myself. So here are a few things that I need someone in this room to innovate so we can make this happen. I need lots of magnets. The technology doesn't exist. Someone in the room needs to innovate this, and I need 11,000 kilometers worth of them. I need a space transport system, and I don't want this goofy SpaceX thing where it kind of goes up and then it comes down, and I need a better big thing to carry people and equipment several times a day. I also need some kind of tunnel scouting and digging, because if we want to dig a tunnel, maybe we, it's going to take a lot of extra resources that we don't have. Maybe we don't need to have tunnel scouting by people. Maybe we just need robots. I see some robotics things in here. Someone can actually invent robots to do this for us. But maybe we don't need to dig a tunnel. Just put it on the surface and put some shielding up on top. Maybe that's easier. We need the next generation of particle detectors. We need more data science and AI and machine learning techniques that currently don't exist. We need a robust moon-to-earth communication system that's robust against solar flares. We need next generation power. Is it going to be nuclear or will it be solar? We need everything else I haven't thought of yet. But would that be enough? If we build the moon collider, would that satisfy me? No. To really do it right, to really answer this question definitively, we would need to reach an energy scale that is so high that everything would be revealed. It's called the Planck scale. And this is the scale at which everything would be revealed. We would understand everything about quantum mechanics, gravity, dark matter, the Higgs boson, everything about neutrinos, and yes, time, and yes, we would probably understand if we live in a multiverse. But to reach this Planck energy, we would need to build a particle collider like the Large Hadron Collider around the outer edge of the solar system. Clearly, we're going to need some major innovation to make this happen, but Luckily, we're at Digital Thailand Big Bang, which is filled with people that aspire to be world-changing innovators. So catch me afterwards, and we'll brainstorm some ways to make this happen. But when we build the ultimate Hadron Collider, and we will, what will we do with the answers that we get from it? Even if we were to find overwhelming circumstantial evidence that you and I live in a multiverse, there's still probably no way for me to ever contact another universe. Such a concept makes no sense. So does that mean such questions are meaningless? You may say yes, and in fact, some scientists would agree with you. And in fact, some scientists cast doubt and attack our efforts to build bigger colliders to try to answer these questions and to investigate them, saying that such questions are non-scientific. But is that true? We started from known science, observations of the world around us, and we followed the chain of logic to arrive at the startling conclusion that we may live in a multiverse. It's a frankly bizarre conclusion, but it's clearly scientific. Just because we can't answer the question now doesn't mean we never will. Things like the Moon Collider seems like it's a few decades ago it would have been impossible, but now it's just regular impossible. And regular impossible we can do. Regular impossible is only impossible right up until the moment when someone makes it possible. So why do certain people object to questions like this? Are they afraid of the answer? And is this the same fear that caused people in the past to object to similar questions like, is the Earth really at the center of the solar system, or are the stars painted on a solid dome a few kilometers above our heads? The fear that you and I are not as special as we think we are. Does this same fear affect you? What might happen if you quit your current safe day job and instead did that big thing that you've been thinking about for years, like starting a humanitarian organization to help people displaced by war or conflict? What might happen if you stopped what you're doing now and instead came to join us to work at CERN, working on the next generation of particle physics accelerator? All of that crazy stuff I said about a moon collider or a solar system collider, it's all based upon current technologies extrapolated to the future. But these technologies are decades old. Plans are underway right now for something called plasma Wakefield technology, which just means a brand new way to accelerate particles to much higher speeds in a much shorter distance. We probably won't even need the solar system collider, but we'll never get there unless other people come to join us. And I can say this because I don't actually work on this. It's okay for me to advertise this for you. What might happen if you did this to join some of the brightest minds in the world to help us understand better how to explore the mysteries of nature? What might happen, for those of you that are in digital or tech or something like that, what might happen if you stopped working on a long string of smartphone apps and instead work on some bigger thing like figuring out how to solve poverty or figuring out how to treat every single human with dignity, love, and respect? The answer to all of these questions is quite possibly nothing, but you currently don't know that, and you never will unless you take the leap and find out. And to me, the safety of ignorance will never compete with the terrifying joy and scary beauty of knowledge. Always ask the big question. Always allow yourself the bravery of stepping into the unknown. And always seek out new knowledge to vanquish and get rid of this fear. Because you know what? This fear distracts us from some of the objective truths of physical reality. You and I don't need to be afraid of big questions. We don't need to be afraid of a multitude of universes because at the end of the day, we know one thing for sure. There is at least one universe. And when you and I, humans, ask questions about the universe around us, we, humans, are the method by which the universe asks questions about itself. And when I see people all over the world irrationally blaming their problems on other people that live in other countries that are displaced by war or are trying to find solace, and when I see that the richest among us are getting richer and richer and the poorest among us are being left behind, and when I see how decades of uncontrolled extraction of fossil fuels are ruining our only atmosphere, and we're not acting fast enough to fix it, and when I think about my friend Melody and how the other kids would make fun of her, and how this made it difficult for her to go to school, and how she never went to high school and dropped out, I feel anger. Not just regular anger. Oh, I feel regular anger too, but as a physicist, I feel an extra layer of anger because I see that when we allow such things to happen, we're betraying a cosmic truth. That you and I are all parts of the same universe, and we're all in this universe together. And so back on those red rocks in Utah, when I was 8 years old, I said to my friend Melody, everything is terrifying. And she said, yeah, it's scary, but it would be scarier if I were out here by myself. And I looked at her and I said, yeah. And we both looked up at the sky, the stars and galaxies watching us from very far away. Thanks.